If you type a number 1 on your keyboard right now,
Yep.
and someone sitting in an office in Tokyo types a number 1, your computer fundamentally believes those are two entirely different objects.
Right, which is so counterintuitive.
It really is. Visually, they might look nearly identical on your screen. Conceptually, both of you mean the singular integer between 0 and 2.
Exactly.
But down at the very bottom of the machine where the actual thinking happens, those two numbers share absolutely nothing in common.
Nothing at all.
Today, we are looking at a bug in a piece of code that proves just how messy human history really is. And, well, why teaching a computer how to read human language is a total unmitigated nightmare. Welcome to the deep dive.
Thanks for having me. And yeah, it is a perfect collision of logic and chaos.
So true.
We are unpacking a highly specific, very technical log today. Specifically, it's part 93 of this massive ongoing series of notes.
R93, yeah.
Right. And it's focused on the Haskell programming language. The entry itself is titled, Refining Chinese Chapter Detection.
Which, sounds incredibly niche, right? Oh, super niche. But while it sounds like it's just about a hyper-specific coding problem, it actually exposes this massive invisible gap between our human intuition and strict machine logic.
Because to a human, reading is just absorbing concepts. You see a blank page, a bold number at the top, and your brain instantly shifts gears like, okay, new chapter.
Exactly. You don't even think about it.
You don't.
Yeah.
But to a computer, reading isn't about concepts at all. It's about navigating this incredibly chaotic landscape of human assumptions, and it's trying to do that using nothing but rigid math.
Which is really where Haskell comes into the picture.
Right, because from what I understand, Haskell isn't just your run-of-the-mill programming language. It is famously almost aggressively strict.
That is the crucial context here, yeah. Haskell is what we call a purely functional programming language.
Okay, what does that actually mean in practice? Well, most common languages give the computer a list of commands to execute step by step. And they allow for a lot of flexibility or, sloppiness, depending on how you look at it.
They let you get away with murder, basically.
Pretty much. But Haskell is based entirely on mathematical functions. It demands absolute certainty.
So no ambiguity at all.
None. You cannot leave things vague. It forces the programmer to explicitly define every single possible state a piece of data could be in.
Wow.
So when you take a language that demands mathematical perfection and you force it to parse human language,
which is just full of slang and typos.
Slang, typos, and thousands of years of shifting cultural formatting, yeah. The friction is just immediate and spectacular.
Which brings us to the specific bug documented in this source material. Because, to understand how a computer reads, we first have to see how it spectacularly fails at reading.
Right. And the program in question here is a parser.
Right. And the whole job of a parser is to take a giant, messy string of text and break it down into categorized buckets.
Exactly. It looks at a document and attempts to tag things like this is a title, this is a standard paragraph, this is a chapter heading.
And to achieve that categorization, the parser needs boundaries. It needs rules.
It absolutely needs rules. And the initial rules set up for finding a chapter heading in this specific Chinese text, it was purely structural.
Okay.
The parser was instructed to look for a specific starting character. The character is D, which translates roughly to number, or it indicates a sequence in a series.
So basically the equivalent of writing number 1 or sequence 1?
Precisely. Then the rule told the parser to scan forward until it hit a closing character, which is meaning chapter.
Okay, I'm with you.
So if the text on the page reads me1, the machine flags it. It sees the opening bracket, it sees the closing bracket, and it neatly categorizes everything inside that container as chapter 1.
Okay, let's unpack this for a second. It's like driving down a highway waiting for a stop sign.
Oh, that's a good way to look at it.
The rule is simple, right? Keep driving until you see the red octagon. Once you hit the red octagon, you know you've reached the end of the trip.
Right.
But the source documents a massive vulnerability in this logic. What happens if the text is a little sloppy?
Which it always is.
Always. What happens if the line starts with B1, but whoever wrote the text just forgot to type the closing get? The stop sign blew over in a storm.
Well, this is the problem. The machine doesn't have the common sense to look at the surrounding context, realize it's in the middle of a new town, and stop driving.
It just keeps going.
It just keeps accelerating. In computer science, this is known as a greedy parser.
A greedy parser, so it just starts eating the document.
It consumes everything. Because the closing boundary was never met, the rule remains unsatisfied.
Oh, wow.
Yeah, so the computer reads past the missing tag, assumes the chapter title is just really, really long and indiscriminately consumes the rest of the line. Then the next sentence, and sometimes the entire following paragraph.
Just treating a massive block of normal text as one gigantic chapter heading.
Exactly. The greedy parser eats and eats because a single byte of data, literally one missing character, wasn't where it was supposed to be.
It really shows how fragile code is. I mean, one tiny typo by a human completely obliterates the machine's ability to categorize reality.
It's terrifying when you think about it.
It is. And because you can never guarantee that a human will type perfectly formatted text every single time, the parser can't rely on those structural bookends anymore.
Right, the stop signs are just too unreliable.
So the system has to adapt. It has to stop looking at the container and start analyzing the contents themselves. It basically has to learn what a chapter number actually looks like.
Which is a huge fundamental shift in logic.
Yeah.
The source details the fix for this greedy parser. It's a brand new utility function named is Chinese numeral or digit.
Okay.
Instead of blindly scanning for a closing character, the parser is now trained to explicitly identify the specific numerical value of the chapter.
But here's where it gets really interesting to me. If the system just needs to find a number, why build an entirely new, complex utility function?
What do you mean?
Well, I would assume, is this a number, is the easiest question a computer could possibly answer. You're just looking for a 1, a 2, maybe Roman numerals if it's an older book. What is so complicated about a digit?
Ah, right. Because to a computer, a number isn't a shape on a screen.
Right.
It's a highly specific numeric byte code. And human beings have spent centuries inventing wildly different ways to encode the concept of 1.
Oh, I see.
Yeah, so this is the Chinese numeral or digit function, has to account for all of that historical baggage. It starts with standard Western digits, like the typical 1, 2, 3 that you find on a standard U.S. keyboard.
Okay, standard or path.
Under the hood, the computer reads the Western digit 1 as a specific hexadecimal value. Let's say it's 0x00 theta 1.
Right, the literal machine language.
Exactly. But then the function also has to actively search for full-width Unicode digits.
Okay, wait, you'll have to explain full width. To a regular reader, a number is just a number. What makes it full width?
Right, so it comes down to digital typography and the history of East Asian typesetting.
Okay.
Traditional Chinese and Japanese text is often designed to be read in a grid, either horizontally or vertically, and every single character occupies the exact same square of physical space.
Oh, like every letter has its own identical little apartment?
That's a great analogy.
Right.
It creates this beautiful, uniform block of text.
Right.
But standard Western letters and numbers are proportional. An I or a 1 is very narrow, while a W or an 8 is much wider.
Right, they take up different amounts of space on the line.
Exactly. So if you drop a narrow Western 1 into a grid of complex, dense Chinese characters, it breaks the visual formatting. The grid is ruined.
Ah, it misaligns everything.
Yes. So, typographers created full-width characters. A full-width 1 is digitally stretched and padded with empty space so that it takes up the exact same square width as a complex character.
So visually, it just looks like a slightly fatter number 1.
Visually, yes. But structurally, computationally, it is an entirely different entity.
Really?
Yeah. The computer doesn't see a fatter shape. It sees an entirely different byte code, like 0 weak FF1.
Oh, wow.
If your code only tells the machine to look for the standard Western 0x0031, it will scan right past the full-width digit and see absolutely nothing.
It'll be completely blind to it.
Totally blind.
So the system is being forced to learn typographical history just to find chapter 1.
Exactly.
And the source notes, it doesn't even stop there, right? The function also has to be explicitly programmed to recognize simplified Chinese numerals and EAD, traditional Chinese numerals.
Right, because the text being parsed could be from a modern blog post using simplified characters. Or it could be a digitized historical document using traditional, highly complex characters.
Which are completely different visually and computationally.
Exactly. Some of those traditional characters were historically used in financial documents, specifically because their complexity made them harder to forge.
That's fascinating.
The parser has to cross-reference all of these cultural layers.
It really exposes the arrogance we have about our own language, doesn't it? We assume a number is just this universal truth.
We do.
But we're forcing this incredibly rigid, mathematically pure system, this Haskell parser, to accommodate the sheer chaotic variety of human expression. We've invented dozens of ways to say one, and the machine has to be painstakingly introduced, byte by byte, to every single variation.
What's fascinating here is how much heavy lifting the human brain does in the background. You synthesize typography, context, and historical linguistic shifts in a fraction of a second without even noticing.
Right, we just read it.
Exactly.
Yeah.
But the machine requires thousands of lines of code to do the exact same thing.
But once the system does learn it, once this Chinese numeral or digit function is fully built and implemented, the boundary is secure.
Yes, fine.
The parser isn't going to get greedy anymore because it knows exactly what a chapter number looks like in every possible format.
It has a perfect definition now.
And what I found so cool in the source material is the ripple effect the single fix has on the rest of the software. Fixing the chapter rule inadvertently fixes the paragraph rule.
Ah, yes, the beauty of systemic logic. A document is generally an ecosystem of text, right?
Right.
If a block of text isn't a title, and it isn't a chapter heading, by a process of elimination, it's usually just a standard paragraph.
Makes sense.
Well, the source mentions that before this fix, the system's paragraph parser was basically operating in a state of constant anxiety.
Constant anxiety. I love that. It had to utilize a look-ahead rule. Now, I've heard the term look-ahead in parsing before, but mechanically, what is the computer actually doing when it looks ahead?
Mechanically, a look-ahead is a massive drain on computational resources. Normally, a parser moves through a document linearly, just eating one token of text at a time.
Like a Pac-Man.
Exactly like Pac-Man. But when a look-ahead is implemented, before the parser officially consumes a chunk of text and finalizes it as a paragraph, it halts.
It just stops.
It stops. It holds its current position in memory, peeks ahead at the upcoming characters, and checks them against other rules to make sure it isn't about to make a mistake.
Oh, I see. It's like a nervous driver who doesn't trust the road signs, so they're constantly hitting the brakes and checking their blind spots before they change lanes.
That is exactly what it is.
Like, I think this is a paragraph, but let me just scan the next 20 characters to make absolutely sure the word chapter isn't hiding around the corner.
It is entirely defensive programming. And it exists because the chapter parser was weak.
Right.
When the rule for finding a chapter relied on those flimsy stop signs that could easily blow over, the paragraph parser couldn't trust the boundaries.
It couldn't trust anything.
No, it had to double-check everything, constantly holding multiple possibilities in its memory, which slows the entire system down.
But the new Chinese numeral or digit function changes the ecosystem.
Completely.
Because that chapter rule is now incredibly strict, culturally aware, and mathematically accurate. The anxiety is cured.
Exactly. The source notes that the look-ahead rule for paragraphs becomes totally redundant. If a line of text doesn't perfectly match the new strict definition of a chapter heading, the computer now knows with absolute mathematical certainty that it must be a paragraph.
It doesn't need to peek ahead.
No peeking ahead.
Yeah.
Doesn't need to hold state in memory. It just executes.
The documentation actually points out that this redundant look-ahead code can now be stripped out of the system entirely. I mean, you can leave it in if you want to be overly explicit, but structurally, the scaffolding is no longer necessary.
If we connect this to the bigger picture, there's a profound lesson in systems design. Perfecting a boundary in one area eliminates the need for defensive mechanisms in adjacent areas.
Wow.
When your foundational definitions are solid, the complexity of the entire system drops. Good rules create simplicity.
I really love that concept. The certainty of one system eliminates the anxiety of another. And while we've been deep in the weeds of Haskell code and Unicode bytes and computational memory costs, this underlying philosophy, this meticulous organization and parsing of data, it isn't just restricted to software engineering.
Not at all.
It's a fundamental framework for making sense of the entire universe.
Which becomes incredibly apparent when you zoom out and look at the actual source material this note lives inside.
Oh, absolutely.
The document on Chinese chapter detection is just a single node in a massive interconnected taxonomy.
It is genuinely dizzying. We noted at the top that this was part 93 of the Haskell notes. But looking at the index provided in the source, the scope of the documentation is staggering.
It really is.
There are over 840 individual parts categorized under gardening.
840.
Yeah. There are over 200 parts dedicated to fish keeping. Plus, there are equally deep, hyper-segmented dives into AI, into modern book typesetting, dieting, photography, and other programming languages like Rust and Go.
The taxonomy spans over a decade, from 2011 all the way to 2026. It is an attempt to categorize an entire intellectual life.
And the juxtaposition of the topics is wild. I mean, you can be reading a highly technical breakdown of how a functional programming language processes hexadecimal byte codes, and the very next note in the timeline is about the propagation techniques for variegated Mexican mint,
Right.
or a granular analysis of managing the aggression levels of ram's horn snails, or the chemical balancing act of a goldfish tank. It jumps from the hyperdigital to the hyperorganic without missing a beat.
Well, at first glance, managing a snail and writing a parser seem like entirely different universes.
Yeah, they really do.
But fundamentally, they're the exact same activity.
Okay, how so? Walk me through the connection between a fish tank and a Haskell compiler, because I am trying to see it.
It all comes down to managing closed systems through explicit observation.
Hmm?
A Haskell compiler requires you to define every possible state of a piece of data. If you don't explicitly tell it what a full-width one is, the system crashes.
Right, the greedy parser eats the document.
Exactly. Well, an aquarium is also a closed system.
Yeah.
It has strict underlying variables, ammonia levels, nitrites, pH balances, the dominance hierarchies of specific species.
Oh, I see where you're going with this.
If you put an aggressive ram's horn snail into an unbalanced ecosystem without explicitly understanding the boundaries of its behavior, the biological system crashes.
It gets greedy, so to speak. It consumes resources it shouldn't.
Precisely. Whether you are defining the mathematical rule for a Chinese numeral, or categorizing the light requirements of an aquatic plant, or tracking the truth about icosapent in a specific diet plan, you are engaging in the same fundamental process.
You're taking a chaotic, undefined universe and you are parsing it.
You are identifying the variables, you are defining where the boundaries are.
You're figuring out where the stop signs are in nature, just like you have to in code. It's the act of making the implicit explicit. When the computer lacked explicit instructions for the chapter boundary, it failed. When a person lacks an explicit understanding of the nitrogen cycle in a fish tank, the fish don't survive. We have to teach systems, whether it's a software program or our own understanding of a garden windowsill, how to read the world.
And the discipline required to document it all, segment by segment, for 15 years. That is the ultimate act of parsing.
It really is.
It is an algorithm for understanding reality. Code isn't just typing math at a screen. It's a philosophy of organization that applies to everything from flora to fauna.
It completely reframes the way we interact with information. Let's recap the terrain we've covered today, because we've gone from microscopic byte codes to the entire natural world.
We really have.
We started with a system failure, right? A greedy algorithm that blindly consumed massive blocks of text simply because a human author forgot to type a single closing Chinese character.
Which forced a pivot away from structural boundaries and toward a deep, under-the-hood analysis of the content itself.
Right, which plunged us into the bizarre history of human typography. We realized that a computer doesn't just see a number. It has to process standard digits, full-width Unicode characters padded for East Asian grids, simplified text, and traditional historical numerals.
So much context.
So much. We had to build an incredibly complex tool, the is Chinese numeral or digit function, just to translate the messiness of human culture into the rigid mathematical certainty of Haskell.
And then we observed the systemic ripple effect of that certainty. By building one perfect rule, we eliminated the computationally expensive look-ahead anxiety of the paragraph parser.
Right. The scaffolding fell away, leaving a more efficient, simpler system.
Exactly.
And finally, we zoomed out to the incredible index surrounding this single technical note, from Haskell compilers to variegated Mexican mint and ram's horn snails. We saw that defining strict rules in code is the exact same intellectual muscle we use to categorize, document, and manage the organic ecosystems around us.
It is all ultimately an act of parsing, defining reality so we can interact with it without crashing the system.
Which leaves us with a fascinating thread to pull on as we wrap up today's deep dive. We spent a lot of time talking about how the human brain is the ultimate effortless parser.
It really is.
We read a page, we process the history, the context, the typography, all without breaking a sweat. We are so good at categorizing reality that it feels invisible.
We synthesize the stop signs flawlessly.
Flawlessly. But here is a thought to leave you with. If our brains are these incredibly highly tuned parsing machines, reliant on the categories and stop signs we've built up over a lifetime, what happens when we encounter a piece of reality that we don't have a category for?
Wow.
Right. When you experience a totally unprecedented emotion or strange, shocking life event where the boundaries aren't defined, Do our brains react like that buggy Haskell code? Do we get greedy?
Do we panic and
Yeah.
consume information indiscriminately?
Exactly. Do we let our anxiety completely take over simply because the familiar stop sign is missing?
It begs the question of whether anxiety is just a human look-ahead function, desperately scanning the future because our present boundaries feel weak.
That is a staggering way to look at it. A human look-ahead function. Next time you find your brain spiraling, maybe ask yourself if you're just missing a boundary.
That's a great takeaway.
Thank you so much for joining us on this deep dive. We will catch you on the next one.